In this video lesson, we're going to take a look at applications of quadratic functions. So this is when we have word problems and we need to, first of all, determine what the question is asking and then figure out the best way to answer that question. So hopefully some of you are familiar with marking the text in maybe an English class or social studies class when you're reading a document and you would number the paragraphs. In math, typically we don't have paragraphs for word problems. In our case, we're going to number each sentence, and this would be where we would go back in class and talk about, in this sentence it says XYZ. Well, this first example has one sentence, so we can kind of skip part one. Step two would be, as you're reading, you're going to want to circle any key terms, any word that jumps out at you as being mathematical or will maybe give you a direction to go for solving the problem. You're going to want to circle that. So our question, determine the number of units sold that will yield a maximum revenue. Maximum revenue is jumping out at me as being a key term. We want to maximize the amount of money that we're bringing in. For a health food company, if the model for the revenue is, and of course, anytime we're given an equation, that's going to be a key phrase or term, so to speak, where X is the number of units sold. That, again, is going to be key information. And actually what I'm going to do there is underline that, because step three is underline verbal model. This is a verbal model. It's telling us what exactly X is representing. And then finally, box the question. Now, I kind of did that with the circle the maximum revenue. The whole statement in this case is our question. Determine the number of units sold. That's really what we're going for. Number of units sold. That's what we need to be able to answer when we're done with our math. So in order to do that, you might be thinking, oh my gosh, I have no idea. Maximum revenue. Think about, first of all, parabolas opening up or down. If a parabola opens up, the vertex is a minimum. It's the lowest point on the graph. And you think about the range, y is greater than or equal to, meaning that is the minimum value. All of the other y values are bigger than that. Our equation, we've got 900x minus 0.1x squared. So that x squared term is what gives us our leading coefficient, and that negative 0.1 tells us that our graph opens down. If your quadratic graph opens down, it has a maximum value at the vertex. So just real quickly, a generic sketch of a graph opening down. If we find the x-coordinate of our vertex, that will give us the number of units sold, which is what x represents, that would maximize the revenue. The revenue is the y value. This is in standard form, so to find the coordinates of the vertex in standard form, we use the equation x equals negative b over 2a. Now what some of you might like to do is to rearrange this equation so that it's actually in standard form. So you might want to rewrite it as revenue equals negative 0.1x squared plus 900x. So we have an a value and we have a b value. Our c value is 0. Substituting right here, we've got positive 900 as our b, so the opposite of that would be negative 900. All over 2 times a. A is the lead coefficient, or what we're multiplying by our x squared, so negative 0.1. And when we evaluate that, we get 4,500, or 4,500 units sold. Always make sure that you label your answer with appropriate units. In this case, units is units. All of these are application problems, so I'm just going to make one long video instead of 3 short videos for each separate question. So we're going to start again by marking the text, number each sentence. In this case, we have 2 sentences, so we might as well number them. 1, 2. Circle key terms. A car's gas mileage is modeled by the function. Actually, I'm going to, this is our mathematical or our verbal model. Number 3, where P is the car's speed in miles per hour, so we need to know that. And M of P is miles per gallon. So again, those are verbal models as well. Key terms, you could talk or circle gas mileage. That's one of the key terms. And then P is car speed, so we have that underlined. Boxing the question, that's all of sentence 2. What is the car's best gas mileage? So I'm going to box actually 2 questions because there's 2 pieces of information that we need to answer in this one. What is the car's best gas mileage, and at what speed is it attained? So we need both a speed and a gas mileage on this one. Same thing, we're looking for the vertex. The highest point, again, this is a graph that opens down, we can tell because our lead coefficient is negative. So the maximum gas mileage will be at the vertex, that will be the y-coordinate of the vertex, and the speed would be the x-coordinate of the vertex. That's the p-value in this case. Again, it's in standard form, so we're going to use that same formula. X equals the opposite of b over 2a. In this case, our b value is positive 3, so we're going to have negative 3 over 2 times our a value is negative 1/28. When you punch this into your calculator, make sure you've got order of operations correctly, that you're multiplying these before you divide. So you may need to use brackets or an additional set of parentheses around your denominator. So I got an x value of 42 miles per hour, or sorry, a p-value, actually I used the wrong variable there. That gives us the speed, again right here where p is the car's speed in miles per hour. So this car gets its best gas mileage at 42 miles per hour. So for those of you that are drivers, think about how fast you normally drive and what that does to your gas mileage. To find the actual gas mileage, we are going to substitute that back into the function. And I would write all of this out, except for that will take me forever. So I'm replacing p with 42 everywhere we see a p in the function. Again, just punch this into your calculator, but make sure that you are using appropriate order of operations. You may need parentheses around this fraction. Make sure it's squaring your 42. And if you do not get 32 miles per gallon, always label your answers. Let me know and I can help you use your calculator more effectively. Last question. This one's a little bit trickier. We actually have to set up the equation on this one. All right, marking the text, we've got 2 sentences. Circling any key terms. So this information obviously is important. We have 140 feet of fencing. We're trying to enclose a vegetable garden. Underline any verbal models. We really don't have any verbal models in this one. Boxing the question, we are looking for the largest area. So we have to create the model. Because we're trying to maximize area, that's what we need to come up with an equation for. We're talking about fencing in vegetable gardens. We're going to assume it's a rectangular lot. Area would be length times width. This is the only key piece of information we have, and this is going to give us everything we need to set up our area model. We have 140 feet of fencing. That gives us the perimeter of the fence. Remember, perimeter is 2 times length plus 2 times width. If you think about a rectangle, we have length times plus width plus length plus width to get the perimeter. So I'm going to substitute 140 for the perimeter. And what I need over here in this area model, I have 3 variables. I can only have 2 variables when I'm trying to come up with a function. So I'm going to solve this for either the length or the width. That doesn't matter because L is a harder variable to work with. I actually want to get that out of there. So I'm going to solve for L so that I'm going to go over here and substitute and replace L with an expression that's equal to W. So solving for L, I'm going to subtract 2W from both sides. And dividing everything by 2, I'm going to divide this term and this term by 2. That'll give me 70 minus W equals L. So what I'm going to do is I'm going to take this expression for L and I'm going to put it into my area model. So the area of our garden will be length, or 70 minus W, times width. So now we have one function with 2 variables, a W variable and an area variable. So I'm going to put this into standard form, distributing that W. And then I can maximize the area the same way that I maximized area in the last two equations. So finding the, in this case, the W coordinate of the vertex, that will be the opposite of B over 2A. B in this case is our 70 because this is written in not standard form, it's backwards. So we have negative 70 all over 2 times our lead coefficient, in this case is negative 1. Negative 70 divided by negative 2 is a positive 35. So if our width is 35 feet, that will maximize the area. The question is, what are the dimensions? So we also need to know the length. So that's where we're going to take this 35, which is W, and substitute it back into this expression that we originally solved for our length. Well, 70 minus 35 is also 35 feet. So in this case, a square will maximize the area. And your U-try. If you're a little bit unsure of how to set up your equation, again, on that video quiz, please just let me know where you got stuck. Tell me how far you got and what additional questions you have to do well on this topic.